Hi everyone. So today we are going to be covering section 12.1 from the textbook, which covers parametric equations. So the three sections that we're going to be covering in chapter 12, so 12.1, 12.2, and 12.3, all of these are very powerful tools that you will use a lot in Calculus 3 if all of you do take Calculus 3. So these are just going to be more of brief introductions to the subject, and then in Calculus 3 you'll talk a lot more about how you actually use these for very specific calculus problems. Okay. So the big idea behind these parametric equations is that it allows you to introduce a time variable to things. So what I mean by this is instead of representing all of our coordinates x, y as f of x, x and f of x, where our y then depends on what our x value is, what we're going to do now is we're going to represent all of them as x of t. So the place we are on the x-axis will vary with our t variable, which is often thought about as time, and y of t. Okay, so let's just jump straight into an example of this. So let's say I have x equals 2t, y equals 1/2 t squared minus 4, and 0 less than or equal to t less than or equal to 8. The other common part of these parametric equations right here is some bound on your time variable. This is not necessarily always the case, but more often than not you'll see limited range in your t variable. And this allows us to deal more with segments rather than the entire graph itself. So let's talk about graphing this. Okay, so we're looking at the time variables between 0 and 8, so let's plug in 0 in for this equation. If I have t equals 0, I'm going to get an x value of 0, right? 2 times 0 is 0, and a y value of negative 4, right? 1/2 times 0 squared minus 4. Okay. Well, let's plug in some more values. I'm just going to plug in even values so I don't have to plug in quite as many of them. So for plugging in 2, I am going to get an x value of 4 right here. And I am going to get a y value of 2 squared. So this is 4 divided by 2 is 2 minus 4 is negative 2. T equals 4, right? X value of 8. And now we have a y value of 8 minus 4, which is going to be 4. Okay, continuing on, t equals 6. Now I have an x value of 12 and a y value of 36 over 2, or 18 minus 4 is 12. And finally, t equals 8. Right, 16 for my x value, and now 32 minus 4 are 28 for my y value. Okay, so let's draw a graph of what this is going to look like. So I'm interested in y values that go from negative 4 all the way up to 28, so like this, and x values that go from 0 to 16, so 4, 8, 12, and 16. So at 0, I have a value of negative 4. Let's negative 4, 4, 8, 12, 16, 20, 24, 28. Okay. At 0, I have a y value of negative 4. Right there. At 4, negative 2. So right there. 8 is 4. 12 is 12. And 16 is all the way up at 28. So we can see that it follows this kind of parabolic type shape here, where it's getting steeper and steeper as we go up. And we'll actually show in a little bit that this is a parabola in this case. No arrows, right? So we're only interested in t-values from 0 to 8. So this is what our graph looks like. Okay, so parametric equations allow us to do another thing as well. It allows us to introduce what's called an orientation, specifically what's called the positive orientation. And the best way to think about positive orientation is going to be the way you move as time increases. You move as time increases. Great, so in this graph here, t equals 0 is down here, then t equals 2, t equals 4, t equals 6, and t equals 8. So my positive orientation is just going to be going from left to right in this graph right here. Okay, great. So we'll talk about one more quick thing with this one, and then we'll move on to a couple of specific examples. Specifically, after this introduction, I'm going to cover circles, line segments, and derivatives. Okay. So the last thing we want to talk about in this kind of introduction section is getting from parametric equations to regular equations. So I have x equals 2t, y equals 1/2 t squared minus 4, t squared minus 4. Well, in this case right here, right, what I can do is I can solve for t. So I have t equals x over 2. And then I can plug this in, right? So I have y equals 1/2 x over 2 squared minus 4, which simplifies to x squared over 8 minus 4. And the other thing I need to change, right, is my bound. So 0 less than or equal to t less than or equal to 8. Replacing t by x over 2, 0, 8, I'm going to see that I have 0 less than or equal to x less than or equal to 16. Which makes perfect sense with this picture right here. If you just look at it, my x values range from 0 down here all the way to 16 over on the far right side. So this x squared over 8 minus 4 and this range right here is going to give us the same equation. Now, with parametric equations, right, there's generally a lot of ways you can write this. So for example, another way I could have written this parametric equation is y equals t squared over 8 minus 4 and x equals t, right? With, again, 0 less than or equal to t, less than or equal to 16. So in general, if you do have a function, it is very easy to convert back into the parametric equation. However, one of the powerful things about parametric equations is they cover a whole lot wider range of different graphs we can look at. So if I just pull up a picture right here, this is from one of the questions in the textbook, and I won't be going through actually doing this problem, how to match these things together. That's just not something we cover in this class. But you can see how absolutely insane and how kind of beautiful all of these curves are that we can get with parametric equations. And all of these are not very difficult equations, right? We have sines and cosines, and we have some t squareds and t cubes, but that's kind of the most complicated that it's going to be. And so they allow us to work with this much wider range of equations. Which is really interesting. And that's kind of one of the main reasons that we use them, in addition to this kind of nice physical application where we can have a time variable. Okay, so the next thing we're going to talk about is circles. And parametric equations basically work on circles very nicely. Okay, so my claim is that x equals r cosine 2 pi of t, y equals r sine 2 pi t, with 0 less than or equal to t less than or equal to 1 is a circle oriented counterclockwise, right? You always need to specify the orientation. So a circle oriented counterclockwise. Okay. Right, so if we think about this, if we did have it being a circle, we'd want something like x squared plus y squared equals r squared. This is going to be our form that we know about for circles. Right, so just looking at what x squared plus y squared is, x squared plus y squared, well, this is r squared cosine squared 2 pi t plus r squared sine squared 2 pi t, right? And Pythagorean's theorem, cosine squared plus sine squared equals 1, our favorite trig identity, so this is going to be r squared. So these two x and y values right here do actually satisfy the equation of a circle. And we can see this also by just plugging in some values. So for example, at t equals 0, right, I get a cosine of 0, which is 1, and a sine of 0, which is 0. So t equals 0 is the point 1, 0. Or sorry, t equals 0. Similarly, if I plug in t equals 1/4, I'm 1/4 of the way around a circle. So this is going to be 0, 1. 1/2 the way around the circle is going to be -1, 0. And finally, t equals 3/4 is going to be 0, -1. And you can see all of these things by plugging them in. So we get this nice circle here. Did not line up nicely with the points. That's okay. So right, I start at 0 and I go around, and so we can also see that this is oriented counterclockwise. Right. So this is just the general equation for a circle. If you do look in the textbook, they also have circles not centered at the origin as well, and these are not very difficult to do either. Okay, so another idea that we have from this is line segments, right? And it turns out line segments are also very easy to do with parametric equations. So the big idea in this line segment section is that if I have a line, it's going to be the form x equals x naught plus at and y equals y naught plus bt, where x naught, a, y naught, and b are all just numbers, right? And t is going to be my variable. And you can also show that this will mean a slope of b over a. Okay, so as a general rule of thumb, when we are dealing with these parametric equations, we will often talk about 0 less than or equal to t less than or equal to 1, which is what we're going to do in this line segment section as well. Now, you don't always have to do it this way. It's just the math works a bit nicer if you're only dealing with zeros and ones, because generally 0 and 1 are easy to plug into functions. Okay, so let's say I have a line from 1, 2, 2, -3, 4. Okay. Just drawing what this is going to look like. 1, 2, 3, 1, 2, 3, 4, 1. So I'm going from 1, 2 to -3, 4. So I would also, in addition to my parametric equation being this line segment, I would like my positive orientation to go this way, right? That's what the from to to means. Okay, so what I want to do in this case is at t equals 0, I'd like to be at my starting point, this 1, 2 right here. Well, this means that x is 1 and y is 2. Coming up to these equations right here, I can see that this means that 1 equals x naught and 2 equals y naught. Great. Yeah, it's going to be just as simple as plugging in t values in order to get this x naught and y naught here. Okay, so this means I am of the form x equals 1 plus at, and y equals 2 plus bt. As I mentioned before, we're going to go to time equals 1. Well, at time equals 1, right, I want x to be negative 3, and I would like y to be 4. So again, plugging in equations, I get negative 3 is 1 plus a, and similarly, I get 4 is equal to 2 plus b. Solving for both of these, I get a equals negative 4 and b equals 2. So my parametric equation is x equals 1 minus 4t, y equals 2 plus 2t, and 0 is less than or equal to t less than or equal to 1. And this right here is going to be the line segment from 1, 2 to negative 3, 4. So just in general, if you are dealing with line segments and parametric equations, consider them to be in this form, and then plug in things until you get all of your x naughts, y naughts, a's, and b's. And also, just for free, right, we know that the slope is going to be this b over the a, so we get that the slope here is going to be 2 over negative 4 or negative 1/2, which we can just get from the parametric equations right here. And you can see this if you do the same trick we talked about before, where you solve for the x's in order to get y in terms of x's and not in terms of t. You would get the slope as b over a. Okay, so we're 2/3 of the way done with the things we said we'd cover for parametric equations. The very last one is going to be derivatives. This may sound scary, but there's actually just a very nice, easy formula for these derivatives. So let's do derivatives. Now the formula for derivatives, dy over dy over dx, so this is derivative of y with respect to x, is going to be the derivative of y with respect to t over the derivative of x with respect to t. Now, in general, right, these signs here don't necessarily mean division, right? dy and dx aren't numbers, they're not variables, they're not anything like that. But one of the beauties of using this notation here is we could see that the dt's would cancel if this was division, and we'd just be left with dy dx right here. So this is why, in general, we use this dy dx notation, is it makes equations like this look very nice and kind of make them a bit more intuitive. But just in general, right, we can't actually do the division right here. This is going to be an extension of the chain rule, and if you use the chain rule, you can actually prove that this is true. I'm not going to go through that right now. All right, let's just do an example of this. Let's say my x is t squared, and my y is 2 square roots of t. Well, dy dt is going to be equal to 1 over the square root of t, right? T to the 1/2. So I'll bring a 1/2 down, which will cancel with the 2, and I'm left with t to the negative 1/2. Similarly, or not similarly, but in the same vein, dx dt is going to be 2t. And so dy dx is just going to be 1 over the square root of t over 2t. Multiplying by 1 over 2t, 1 over 2t, I'm going to get that this is 1 over t to the 3/2. And so what this allows us to do in this case is it allows us to say, okay, if you think back to the very first chapter we talked about, where we talked about velocity and acceleration and position, right? Normally what we would get is we would say, well, my velocity at some position is such and such. But what parametric equations allow us to do is say that my velocity at a certain time is such and such. So you can see that there are a lot of physical applications to these parametric equations. So just one more really quick example before the lecture's over. Let's deal with an ellipse. So an ellipse. You don't need to know this, but an ellipse is given by the equation x equals 4 cosine of t, y equals 16 sine of t, and 0 less than or equal to t less than or equal to 2 pi. This is going to be the equation of an ellipse. And actually, let me just pull up a picture of this. Okay. So it's an ellipse that's a bit skinnier than it is fatter. So just taking these derivatives, right, dx dt is going to be equal to negative 4 sine of t, and dy dt is 16 cosine of t. And so dividing both of these, we're going to get that dy over dx is going to be 16 cosine over negative 4 sine. So this is going to be a negative 4 cotangent of t. Right, and this kind of gives a nice demonstration of how powerful this method is, right? We've never talked about ellipses before. They tend to be fairly difficult to display with Cartesian coordinates, but using parametric equations, we could very easily come up with the slope for different t values of this ellipse right here. All right, thank you for listening.